Hello all, welcome back to the tutorials. So we'll continue our discussion on the operation amplifier. So in the previous videos we have talked about the operational amplifier symbol and then the offset voltage. So we will go little inside to the operational amplifier and see how the internals of it would be. So now we know this is how it looks like. There will be a non-inverting input, inverting input, and the difference between them will be the output. So that means this is VD, if you say, is nothing but this is V out, sorry. VD is nothing but, if you consider one as V1 and V2, so the VD would be amplified and then it will give as the V out. So now we can say that the because the input is the difference between the two voltages. So this can be a differential amplifier configuration where you provide two inputs and then the output would be difference between the two collector terminals of these two transistors. So in this differential amplifier itself there could be two differences. One is like the difference between the collector of two collector terminals of the two sections of differential amplifier, and then a single-ended output. So generally we see in the op amps a single-ended output with a differential output. So this, if you see, we have talked about switches and then how when this transistor is off or on, the current would be drawn. So we have discussed about the NPN, PNP transistor. So the functionality would be the same based on the supply you give. The switches operate and then you get the desired output. Now here basically if you see we have been talking about the very high input impedance of the operational amplifier. So when we say very high input impedance, that means the current would be very less. It would be in the nanoamps or max could go up to microamp. So you can see here this is NPN transistor. For NPN transistor we know that the base current required for this transistor to be on is very less. So you can map this to this circuit and see why the op amp requires a low input current, or why we say that the input impedance of the op amp is high. Now discussing further, so this is the op amp differential amplifier configuration. So here in the previous slide we just talked about a basic differential amplifier circuit, but in the op amp this is how the internal circuit looks like. So here if you see this is called a current mirror circuit. What basically it does is it mirrors the current that is going into this Q1 into this particular section. So that means the current flowing here would be same as the current flowing here, and then there will be some current flowing here, and the output terminal here, if you say this is the output terminal and with the ground, with reference ground, so this we can say I1 minus I2 is the current flowing into the output terminal. So the output terminal could be positive, could be negative, depending on the different configurations you give. If you, whether V1 is provided the input or V2 is provided the input, based on the configurations the output current will vary. So this is how a differential amplifier configuration of op amp looks like. We can one can go and study in depth about this configuration or simulate to see how this is functioning. Discussion. So we talked about the differential amplifier configuration of an op amp. So basically there is one parameter of an op amp called the common mode rejection ratio. So this in brief we have talked like, let us assume for an op amp, okay, we have a plus and minus and we have V0 So now we have V1, V2. So we have seen different scenarios of input to this, where one is a different configuration where you will give V1 and then you will give V2. So now this V1 minus V2 would be given, which is Vd, and then you get a output. So now let us assume I have a input like this, a sine wave, and then there is a input of opposite polarity. Now Vd will be very high here and you get a very high output. Okay, high output in the sense a good level of voltage at the output, not the digital logic. So there is another scenario where you apply a voltage commonly between these two. Now in this scenario we have seen that as same voltage is applied to both the terminals, Vd is equal to V1 minus V2, which is both the same, which is nothing but 0 volts. That means ideally the output voltage is 0, but we have seen there will be some voltage which is called the offset voltage. Now which means in a common mode scenario where you give the same voltage across plus and minus pins of the op amp, the output should be 0. And in a differential mode scenario where you provide different inputs to the plus and minus pins, whether it could be say different polarity, or one could be grounded, or one could be provided a signal, in that scenario you should have a very high voltage. So this means in a common mode scenario the gain should be 0, whereas in a differential mode scenario the gain should be very high for an op amp. If you take the ratio of this differential mode gain to the common mode gain, this is called the common mode rejection ratio of an op amp, which indicates the capability of the operational amplifier to reject the common mode signals. When a common mode signal is applied to the input terminals of an op amp, it should be rejected and the output should be 0. So this is what CMRR indicates. So CMRR is one of the important aspect of op amps to help you know whether to select your op amp in your application or not. So we will discuss more about the operational amplifier configurations in the next videos. Thanks for watching. Please post your comments for our video and let us know your suggestions. Thank you.